Cool. Right. So today this class, so we started from the very basic, you know, image processing exercises. Then we went on to see what, neural networks are. And then we went on to see what CNNs are and how to visualize them. So now you can see that we are moving on towards more sophisticated activities with CNNs. And so today, our main focus would be, these high level tasks like object detection, image segmentation, and yeah, so things like that. So you can understand, like, we started with something so simple, like an MNIST digit classifier, and now what we have to do is, given an image, we have to detect objects in that through a neural network. So CNNs have CNN based object detectors are actually many. So there are so many object detectors available in the market. There are so many. Okay, we wait for 1 minute. Okay. So there are so many object detectors available in the market. So each of them have some use. So the first one, the RCNN one, it is probably the first. It is probably the first of these object detectors. And so if you remember, it's a two-stage object detector where you have a selective search algorithm which outputs some 2000, what do we call it, region proposals, and based on those 2000 region proposals, in the second stage you find the bounding box coordinates and the class of the object. So similarly, fast RCN and faster RCN, all these three are basically nothing but two-stage object detectors. So fast RCNN is a little bit faster than RCNN, because what RCNN does is, if you remember, so there are you use the selective search algorithm to find the region proposals, and then you run a CNN through each of those region proposals separately. Um, to find to find features, basically image features. So that is why RCNN is pretty slow. Fast RCNN uh, does this just once, so it just passes the entire image through a CNN to get the features, and then it proceeds just like RCNN. So it finds what are the region proposals using selective search, and then it goes on just like RCNN. Faster RCNN is nothing but they have now, um, what do we call it? They have now replaced the selective search algorithm with a machine learning based algorithm. So even now you are the region proposals also you are learning through the network only. So now there's a trade-off. So these models, RCNN, fast RCNN, faster RCNN, they are very effective, they are very accurate, so they can very accurately find objects in your image. But suppose you want to use your mobile phone to detect objects, or suppose when your camera detects faces, you can't be slow with that. You cannot hold your camera onto some scenery and wait for ages for the camera to detect the objects. That is why people also came up with some faster object detection methods like YOLO and SSD, which are not too short but single shot object detectors. With the the goal was that, okay, fine, I can um, you know I can still not detect, maybe fail to detect one or two objects, but I'll do it fast. So there's always a trade-off in everything that you do in deep learning. There'll be always a trade-off, that do you want it to be fast or do you want it to be accurate, and you have to arrive at a sweet spot with every model that you have. So YOLO and SSD are the ones that we'll probably go through today, and both of these are single shot object detectors where the goal is that even if we miss out one or two objects, we have to do it very fast. So we cannot do it in two stages like these are the RCNN family. We'll have to do it in a single stage. So what is YOLO basically? How does so surprising thing is that both YOLO and SSD they manage to detect objects in one shot, in one pass, right? So how do they do that? So we'll give you a very rough idea of how it's happening, but you'll have to read back and read back more because these processes are very intense. So right. So what happens is that suppose you have been given an image. So you can see that there's this dog, there's this cycle, there's this car. So multiple objects are there. Even the tree is there, the background is there. So many things are there which you have to detect. Now the uh, the motto of an object detector is twofold. One is you have to detect per object you have to detect a bounding box. That is point number one. So in order to detect the bounding box, what do you need? Basically, if you suppose you want to draw a bounding box around this dog, what you need is basically the coordinates of the bounding box, the coordinates of the four corners of the bounding box. So that is something you need. And also you need to know if you are detecting objects like whatever you have detected, what object is that? Whether it's a dog or a cat or a truck or what. So these are the two objectives that are main objectives that are there in a object detector, right? So how does YOLO function? YOLO basically divides the image into grids. Okay, so it's like this. So it's very similar to how you divide the image into patches for CNNs to work and all. So so you divide it into equal sized grids. So suppose and you have an S cross S grid here in the image, and most of the times it's like a 7 cross 7 or 14 cross 14 grids. That's how you divide the image. So you can see that there are these 7 cells across the rows and 7 cells across the columns. So uh, in all you have some 7 cross 7, that is 49 grids in this entire image. So now that you have found these grid now that you have divided the image into grids, your next task would be take each grid and first of all try to find out the moral of the story is that take each grid and try to find out whether there's an object in this grid or not, and if there is an object, what is the object and what is the confidence of that object. So that is the moral of the story, that for every grid you are basically trying to find whether that grid is part of an object or not, right? So how it happens is something like this. So I'm sure if you have gone through RCNN, you are aware of the concept of anchors. So anchors are basically predefined set of bounding boxes. So what you'll do is for take a cell like this, and keeping this cell as the center, you'll try to draw bounding boxes based on the anchors. Yeah, right. So yeah, so on the given cell, keeping that as the center, you'll try to draw all the bounding boxes that are there based on the anchors. Suppose you have some K anchors. K can be anything. Generally in RCNN, it's like something like 9. I've forgotten what it is for YOLO. Might be something similar. So these K anchors you are drawing around your around your bounding box, keeping around your cell, keeping it as the center. And then what you're trying to do is, so as I said, for bounding boxes, what you need to do is, um, even though you have these K anchors, what you want is for to detect the perfect bounding box. And to detect the perfect bounding box, what do you need? You want the detected bounding boxes to be as close to the ground truth as possible. So that is why you'll require their coordinates of the four corners, okay, of the bounding box. So your coordinates of the you have to, for each anchor you have to determine what is the coordinate of each, each of them, and also the confidence, like whether that is a, how likely is this particular anchor a bounding box, right? So this is what you do for each grid. So in this one pass, you are just realize that you are finding out all the bounding boxes that are there. So yeah, obviously by this you'll get many bounding boxes, and probably there will be a thresholding scheme based on which. So here, like for example, you are getting bounding boxes plus confidence. Again, by confidence what I mean is that, um, what how likely is a particular bounding box or a particular anchor, how likely is that a true bounding box given based on your ground truth. Okay, so you are getting many such boxes. See here, some of them are very deep, some of them are very light, they are hardly visible. So for the more the bounding box borders are deeper, that means it's the model is more confident that this is a true bounding box, right? And if it's lighter, if the edges are very light, that means it's not very confident. So based on this confidence, you can place a threshold and you can pick up some of the relevant bounding boxes. So just note here that since here in the ground truth there are three objects, the dog, the cycle, and the car. So you'll see that for all of these, the borders are very thick compared to the other bounding boxes, uh, other detected bounding boxes. So that is where you detect the bounding box. Now the second, okay, just a second. Yeah. Okay, for the second case, so bounding box is one part of it. Second part is to detect the class. So again, what you do is, since you have divided the image into a grid of S cross S size, what you do is for each cell in the grid, you also try to um, find the probability of each class. Suppose you have a predefined list of possible objects like dog, cat, tiger, cycle, car, and whatnot. Some maybe, suppose 100 objects are there in your data set. So what you have to do is, for each, take each such grid, each such cell, and then you try to find out, you make the network learn what is the class that this grid belongs to. For example, in the true image, this grid belongs to the dog class. This grid belongs to the dog class. This grid belongs to the dog class. So hence, all these grids that are marked in blue, they are basically belonging to the dog class. Similarly, the cycle grids, the model has to learn that these cells belong to the cycle class. These cells belong to the car class, and so on. So this is how basically you, in one pass, you have to learn the bounding boxes and their confidences plus the class probability map. So this class probability will basically tell you, like, what is the what is the class that is present in this region. So here it's dog, here it's cycle, here it's, in this area it's car. So this map will basically tell you in what part of the image what object is present. So this is more or less about YOLO. Again, this is a very short description. You should go back and look at it in a bit more detail, but just some mathematical um, details here. So first of all, as I said, you break the image into this S cross S grid, and for each such cell, you try to place the K anchor boxes. So there are K anchor boxes, and suppose, as I said, like I said, 100 classes might be there. So let's call it C, right? So for each, what you'll have is, for each cell, as I said, you are trying to place K anchors, and for those K anchors, each of those K anchors, what are you trying to predict? The coordinates of the bounding boxes and the confidence, right? So coordinates means there are 4 values and confidence means 5 values, right? So that is why it says that number of desired outputs is S cross S cross K into 5. K into 5 means for each there are K anchors, and for each anchors you want 5 outputs. That is why K into 5 plus C. C means what? That C is the number of classes. Suppose 100 classes like dog, cat, etc. And for each of those 100 classes, you want the confidences. what is the confidence, what is the probability of the object being a dog, or I mean the cell belonging to a dog class or a cat class or a truck class, etc. So this is the number of outputs that you get from the model. So similarly, there is another single shot detector which is very popular. This is called SSD. So it's kind of, the functionality is kind of similar to YOLO, but it happens in a little bit different way. So as it says here, you have multi-scale feature maps for detection. So at every stage, you have this input image. Now you start off with a okay. So yeah, you start off with an image, and there's a feature map of this size. Then there's a feature map of a smaller size. Then of another smaller size, smaller size, smaller size, until this is very small. So we all know that the I mean the low level I mean the feature maps which are there in the beginning of the network, they are there to detect very fine, features, low level features. Yeah, so they are there to detect low level features in your image. And as you go deep into the network, as the resolution becomes smaller, you are looking at, I mean, your receptive field is becoming bigger and bigger, which means that you are looking at the high level features of the image. So this is why probably they do this, is to detect, objects of different resolutions and different sizes. So what they do is, so suppose yeah, so they have a feature map, like suppose this feature map is of this size. Now, based on the output features, whatever this feature map outputs, you try to predict your objects from here. Then from the next, okay, this is getting interrupted. Right. So then for the take the next size of the feature map, and you attach another classifier here. Classifier means what? So it has, suppose it's trying to detect classes, whatever classes, number of classes are there, and the four bounding box coordinates. So that is what it tries to do. And similarly, as and so basically the moral of the story is, as and when you go down on the feature map size, you attach a classifier to all of them, right? And the idea is that you decrease the feature map size, and as that decreases towards the right, the scale of the detected objects increase. Why? Because as and when you are, so if you have read through the deep CNNs, so the lower ones means the ones that are there in the beginning, they look at small things in the image. So for example, last day I talked about things like detecting edges and corners and small things like that, and they begin with that, and as you go towards the right, it starts looking at the holistic image, the whole image maybe. So that is why uh, you you go on decreasing the, I mean, in the initial part of the network, probably it's detecting, small scale objects. And as the network size, as you go towards the right in this deep CNN, your object sizes, you are able to detect bigger objects. So that is what is being done here. So the moral is that you attach a classifier to each, basically you use each and every one of them to detect objects. So that is just what is happening in the SSD. And in the process of doing that, basically you detect a lot of what do you call it, it's like there's a lot of wrong detections or overlapping detections and so on. So it's like so let me, yeah, suppose the situation is like this, that your model has detected something like this, that for this phase it has detected it has given actually 4 5 bounding boxes which you do not need, right? So it has given many noisy bounding boxes, and now what you have to do is you'll have to get rid of them. So how does this happen here again in the yeah, inside SSD there's a little bit of example on that. So suppose there's this image given and you have a cat and you have a dog like this. These are your suppose bounding boxes. So what you are trying to do here is, I think the main algorithm is very similar to YOLO, but suppose you have this image and now you have a 8 cross 8 feature map, right? And on this feature map you are again like YOLO, you are at a single shot, you are trying to detect the bounding boxes first and the class probability. So it's like this, that yeah, you are trying to detect it here, and I mean at every grid you are trying to detect the bounding boxes just like YOLO. It's not very different. And similarly, so this is for the 8 cross 8 feature map. And now when you have a 4 cross 4 feature map, your receptive field has increased. That's why see the cell sizes have increased. So again here also you are trying to detect your um, um, what do we call it, yeah, here also you are trying to detect your objects. So here basically you are able to detect, so it's like the one that is given here. So see the cat image is very, cat object is smaller, right? So the 8 cross 8 feature map is able to detect the cat. So either the blue bounding boxes, so either the square one or the rectangular one, they are able to cover the cat. And now for the, when you have the 4 cross 4 feature map, what happens is each cell is actually looking at a much larger part of the image, right? So that is why now the in the 4 cross 4 feature map, if you detect objects in each cell, you are able to detect the dog. That is why they do this kind of an architecture, where they have this kind of an architecture, whether they are where they are trying to detect objects at basically every convolution layer in the network. So right. So now, yeah, so we talked about this, that whenever some images, some object is detected, so there might be multiple bounding boxes that are describing the same object that are basically noisy. You do not need to keep all those bounding boxes. So there's an algorithm called non-maximum suppression that is used to basically find out the best bounding boxes that can describe your object. So here also it's given, right? So this blue one, there are two blue bounding boxes that are detecting the cat, but we do not need to have two. We can, it's enough to take only one bounding box for the cat. So how to choose which one to take? That is given by this algorithm called non-maximal suppression. So for that, let's first try to look at three matrix basically. So suppose you have been given two bounding boxes B1 and B2. It's very easy. What is the intersection between them? It's this area, which is basically the intersection of these two bounding boxes. Similarly, you find the union of these two bounding boxes, and this will be the entire area, basically the union of the areas of B1 and B2. And now the actual metric that we want to measure is called IOU. You will find it in multiple areas, this IOU being used. So it's called intersection over union. What happens there is that you have found the intersection here, you have found the union over here. So you just find this intersection upon union. That is called the IOU. And so if IOU is basically, this metric is basically used as a thresholding metric. So if IOU for a certain bounding box is high, then you do not keep it, otherwise you keep it. Let's go through the algorithm, it will make it much more clearer. So yeah, as I showed you the image some while back, that in this particular image there's this face and this face, yet see so many bounding boxes are there that are trying to detect this particular face, but we do not need all of them. One, just keeping one would be enough, that describes the face well. So how do we get rid of the unimportant bounding boxes? What we do is, the algorithm is very very simple, that you just select a random box. So suppose you have all these, suppose how many are there, 1 2 3 and 1 2, so five bounding boxes are there in the image, and you select one of them at random. Suppose we select this one, the one that I'm marking, this one, yeah. So select a random box from a bounding box proposal list, compare it with the rest of the boxes. So we compare this, but the one that I chose, this particular one. So I compare it with all the boxes that are there, and I find the IOU with respect to all these other boxes of the box that I chose. And if the IOU is greater than zero point 0.5, that means what? That there's a IOU, if you look at the definition, if it's greater than zero point 0.5, then that means that there's a considerable intersection between those two, which means they are very similar bounding boxes, which also means that if I have such a uh, whatever bounding box I have selected, there are in my bounding box list, there are other bounding boxes which are very similar to this. So I can remove this bounding box from my list. It won't really cause any problem, right? So we go on repeating this until we get a null here. So none of the boxes have IOU greater than zero point 0.5. So in this way, basically, let me admit. In this way, basically, we get rid of the extra bounding boxes and we come up with just, the best bounding boxes that are possible, right? So this is called non-maximal suppression. Again, this is a very, very useful algorithm, and you'll see later in other courses also that this is a very widely used algorithm for different applications. So now, the next task. Now we were detecting objects till now. Object detection means what? That suppose there's a face here. What, again, I'm repeating that what are the requirements of an object detector? That first you detect the objects, whatever objects you find, you put a bounding box around them like this, right? And second, after putting the bounding box, you should also tell that inside the bounding box what object is there. For example, here there is a face. In the previous image, there was a dog, there was a cat, like this. Now, what is the difference between an object detector and an image segmentation? The difference is this, that in image segmentation, we are trying to do almost the same thing, but in a much more complex way. How? Basically, given an image, not only are we trying to detect the objects that are there in the image, we are not going to draw an sorry, we are not going to draw any bounding box around it. This time, we look at each pixel in the image. Just remember, pixel space now. Not any more, not patches, not any grids or anything. Draw pixels. So the image is made up of raw pixels, and for each pixel, we are trying to label them. Label them in the sense what? That suppose there's a pixel here where the red dot, I have placed the red dot. Since this pixel belongs to a car, it should have a certain label. It should have the car label. This pixel, since it belongs to the road, it should belong to the road. It should have a road label. So in this way, whichever pixels are there in the image, based on what object they belong to, they should be classified. So each object should have a class, each pixel should have a class associated with it based on what object it belongs to. So similarly, this is also a brain image where suppose you are trying to look at tumor or something. Then you have, suppose, obviously I do not know brain images, but yeah, suppose your yellow pixels stand for tumors. So basically you have marked this area all the pixels that are there in this area with yellow, some are there with red, some are there with green. So whatever classes you want to detect, you just label every pixel belonging to that class with that label, right? So a very brief summary of how this happens is that, first of all, in this kind of a case, since you are trying to detect every pixel in the image, how do you so you want to train the network, right? So in order to train the network, what do you need? You need the image and you need the ground truth classes also. So one very big problem with image segmentation methods is that for this is a very data hungry approach. Why? Because in order to segment the image, you need you need some annotator to annotate every pixel in the image. So while training, since you need to give the ground truth classes as well, you need to give something like this to the image, to the to the model. So there'll be an original image which will not contain any such classes. It will be the original image, and then there'll be some masked images where you'll basically mark out which are the car class pixels, which are the road class pixels, and so on. And suppose how the ground truth is specifically given is something like this, that suppose you have total 10 objects, right, in your vocabulary, in your data set. And now what you have, in order to mark all those 10 objects, what you'll do is, suppose one object is car, second object is car, sorry, first object is car, second object is road, third object is house, and so on. So for each of these classes, you'll generate a binary mask. So that means what? That suppose you take the first object car. What you do is, you'll generate a, out of this image, you'll generate a binary mask where only the pixel locations where the car is present will be 1, all the others will be 0, right? So that will be a binary mask which will be only for the car object. Similarly, when you are trying to detect the road, what you'll do is, again you'll have a separate uh, binary mask which is of the same size of the image, where all other pixels are black, only the road pixels are white. Similarly, suppose if you have a tree class, then the same thing will happen for the tree. House class, same thing will happen for the houses, and so on. And basically the input for the labels, you'll basically have, if there are C classes, then you'll have C such binary masks in order to represent, like what pixels in the image belong to which class. So now, as I said, in the output, suppose again here take that total number of objects that are possible is 4 in the world, right? And what you want to do is, for in the input, what you have given is the original image in suppose color. So there will be 3 channels, and what you have in the label space is this. Since you have 4 objects, you have these 4 binary masks which are of the same size of the image. Okay, this is your, suppose at this point, suppose this is your y which you want to predict. So each for each class, car, road, house, tree, you'll have all these 4 binary masks that are your ground truth. And because these are your ground truth, you also need to predict them, right? In order to learn the segmentation masks, in order to be able to segment the image, you need to learn these ground truth binary masks. That is why your output, your prediction should be of the same dimension as this one. So since there are 4 objects, you need to predict 4 such masks given an image. And how do you do this? This is done through some architecture called encoder decoder architecture. So basically what you do is, you start with an image which is suppose having 3 channels RGB, and then you go on, you pass it through CNN, normal deep CNN layer, and you know that CNN, as and when you propagate through it, the resolution becomes smaller and smaller in order for you to, for the CNN to capture maximum information. And now suppose you have this particular feature map, activation map. Given this, you are not able to match with your given labels, right, where you have 4 binary masks of the same size as this. So basically what you need is, for the, you have to have, in the output you'll have to have uh, you know uh, some activation map of the same size as this one, right, in order to be able to predict the masks for the individual objects. So that is why normally CNNs do downsampling, which means that the sizes become smaller and smaller. But in this case, there is something called upsampling. So now with the smaller one, you start with the smaller one, and you suddenly start going up in the resolution. So your resolution starts increasing here. So this part is called, this part of the network, this part is called encoder because you are encoding the information. And now this part is called decoder because using the encoded information, you are trying to detect your masks for the individual objects. If there are 4, there will be 4 masks. If there are 60, there will be 60 masks, and so on. So this is called an encoder decoder architecture. And yeah, obviously it's made up of so it's all given here, like what these are made of. These might be conf plus batch norm plus ReLU. The blue ones are pooling, as we know it downsamples the activation maps. And similarly, there's something called upsampling as well, which basically increases your resolution in the activation map. And finally you'll have a softmax layer, which will produce uh, um, the classes, right? So that is how you segment the objects in the image. And this is another variant of the encoder decoder architecture with skip connections. So skip connections, we all know residual connections, skip connections, why they are so useful, we know. So that is why in big networks, in deep CNNs, deep neural networks, keeping skip connections is a very, very common phenomena. So you start with an image. Okay, one thing that I probably didn't mention very clearly in this slide is that uh, at this point, I mean, yeah. So here there are, so this layer is a softmax. Why this is a softmax is because you want to detect probabilities, right? And so you need to do this for, so this is actually, while for giving an example, I said that, these four are all for four different objects, but actually it's not that. You need to detect four different, you know, you need to detect four different activation maps in this way for the four different objects, where your last this particular last box will be a softmax box in order to detect the softmax probabilities, right? So this is what they call a unit architecture. So this is again a very, very popular architecture, where again this is very similar to what we saw here. So there's an encoder and there's a decoder, and basically you have a so for what you do here is that, in order to not lose out the information that is there in this downsampling part or encoder part, what you do is, for each of the matching activation maps, so this activation map matches with this one matches with this one in size, and so on. So what you'll do is, you'll just add a skip connection from here to here, here to here, here to here, and so on, so that the information that you learned across here doesn't get lost while backpropagating. So that is the purpose of skip connections, we know that, and that is why skip connections are added here. And finally you are able to detect the individual uh, masks. So basically, like here it's shown together that there's a red mask and there's a, suppose a green mask, I mean green object and a red object, but actually in reality there'll be like two such masks. One will only detect the red, one will only detect the green. So that is this is called a unit architecture. So
Ma'am, small doubt here. Like
yeah,
the single architecture will predict the two mask, or for each mask we should have the one architecture.
single one will only predict. But yeah, I mean, the input will be something like, um, yeah, so the input will be something like, as if you have a binary mask for each object.
But ma'am, in that case, all weight will be disturbed. No, like taken one architecture of this unit. Suppose we train for two masks, one for cat, one for dog. So
Mm-hmm.
when we was training for the cat, weight will change accordingly. But again, when we are training for the dog, weight will change again change. Weight of the same architecture is getting changed. So how it will detect the both?
Okay, I'll wait. Let me think. What used to happen here? See, as far as I remember, it used to do it for separately for each objects, one mask for each object. Okay, let me wait. Uh,
Ma'am, the doubt is whether one architecture will only
yeah,
give
yeah,
one
yeah,
mask, or one
yeah.
architecture
I
can
got
give
your
multiple
point.
masks.
Yeah, I got your point. So, mhm. Actually, these are so detail specific things. It's very difficult to remember them. But yeah, let me think. What's the logical? So, uh, what was it? Probably used to. Okay. See, one possibility is that this architecture remains same till here, right? And then there'll be multiple heads like this. So multiple classification heads like this, which will, classify your um, so if there are 10 objects, it will classify your there'll be 10 classification heads which are basically finding the 10 masks. That is one option. The second one is that maybe there's only one classification head which will detect all the masks together. So which either this or that. So I'll have to get back to you on what unit exactly uses. So one thing that I can do is, I don't know whether, here in this small time whether I can find it or not. Unit for okay. See, let's do one thing. We'll anyway go through the code of unit. Okay, so there only we'll get what's going on. So let's not waste time here. Well, let's go through the code quickly for unit. So that will tell us. Mm, okay. So I guess this is visible to all of you. If not, I'll just zoom it a little bit. Is it connected? Yeah, connected. Right, let's start running the code one by one. Uh, yeah, some import statements will be there, some helper functions that are always there in order to plot uh, the different images and all. So, yeah, so this code actually is pretty interesting because here actually they generate the data by themselves. So let's have a quick look at how this data gets generated. Let me actually becoming problematic for me if it's so much zoomed. This is better for me. Yeah, so first we'll look at how the data looks like. Yeah, so the data will be something like this, that this will be our original image. So yeah, so this will be your original image. So what are the objects that are present in all? One is the like a square, right? One is a triangle, one is a circle, one is a hollow circle, one is a plus, and one is something called a mesh. So there's a data set that is getting generated. So maybe we'll go through the code of that very quickly. But yeah, there's a data set that is getting generated, and what you need is, in the output you are basically trying to look at so you want to give, so since you want to object detect these objects, basically segment. So this particular code block is for segmentation, note that. So this is for segmentation, where we are going to use a unit like architecture in order to um, you know uh, segment the objects. So what you want in the output is, given this image, you want different distinct colors for each of these objects. Distinct colors means what? That wherever the square pixels are there, you want a separate label for them. Wherever the triangle pixels are there, you want a separate label for them, and so on. This is what is meant by the segmentation task. And what they do here is that how they create the data set is very simple. Actually, this is not very important for you. This is only some code where they are generating some synthetic data in order to generate the kind of images that I showed you. So basically, yeah, this is not very important, but yeah, what they're trying to do in these areas is that I described those six objects to you. So one will be a triangle, then there'll be a circle, then there'll be a hollow circle, mesh, square, plus. So all these um, objects are there, and what you are doing is, since this is a synthetic data, means this is not a real data, we are generating this data just for training purposes. So what they are doing here is that, given an image, they are just finding some random locations where they want to place the triangle, circle, mesh, and so on. And basically, so you can get from the names of the functions that get random location means that returns some random location in the image where you want to put these objects. And now in the then what you do is, based on the given locations that are there, so this triangle location, circle location, you can see that here what you do is, one by one you add the objects into the image based on the location. So again, I keep on repeating that this part is not very important, because here they are just generating a synthetic image. So now uh, then they'll do is they'll create masks. So as I said, masks, look at what mask is basically kind of a list. Okay, this is basically an array, basically a numpy array. So what you have done here is that yeah so what if you look at the function name, what it means is that you have a, suppose what I say, that masks will be binary in nature, where your true object will only have one. The true, wherever the true object is present, only those pixel locations will have one. Otherwise, all pixel locations will have zero. So that is what is done here. So there is one mask for filled square, one mask for circle, triangle, maybe this is the hollow circle, and mesh, plus, and so on. So yeah, so basically, as I said, this one I said correctly, that in the input you'll have basically six different masks for all the six objects. So these are the possible six objects. Maybe your image, all the images might contain all six objects, or they might contain a subset of them. So this is these are how the masks are at least given as input. So we'll, when we go through the unit architecture, we'll know better as to your question, whether what how the unit actually outputs these masks. But yeah, we'll go through that. But yeah, and this is how the data set is created. So this is the crucial part, which you can look at later also, that this is how the masks get created, because these architectures, UNet and I mean image segmentation, object detection, these, what, at least when I learned them, I found them to be confusing, and it actually became much more clearer when I started reading them more and more. So that is why, I mean, this is an important part which tells you how the masks get generated. And so I already ran this piece of code, and you can see that your input image is of this size. So it's a 192 cross 192 cross 3 image, whereas your output is of this size. So again, your height and width will be same, 192 cross 192. But there are now six binary masks because you have six objects. So this is how at least your true ground truth is given, right? And now, so we have plotted this. Right. So now we have a data loader. So data loader, again, just to repeat, the function of a data loader is nothing but this is a faster way that Python gives you, PyTorch gives you to collect your data set and, or I mean, basically, uh, you know, access each of the images and batch them up. If you want to create mini batches of images, this is a fast way to do that. This is how PyTorch wants to organize your data set. So correct. So this is how it is that uh, first of all, in the init function, so keep a practice to write this kind of data loaders, because they'll be handy. So very often you'll need to write your own data loader. So start with an input image. And so basically in the self.input images and self.target masks, you generate all the random data that is there. Suppose you want to create some 20,000 training, say 20,000 training images, then you put all of them into this input images and target images. And suppose if you want to do some augmentations, then you have this you put it in this self dot transform, right? And this get item function basically returns you individual objects in the way that you want. So what you want is, during training you want the image, the raw image, and the mask, right? So that is what this get item returns. So it will take one image after another. Suppose if you have 20,000 images, it will take this index as a as an argument, as a parameter, and this index. So suppose if you want the 100th image, so what it will do is it will take the 100th image, take its mask, and return it. So it will be like an image and the mask together. So now internally what PyTorch does is it keeps calling this function, and very in a very fast manner it will convert your data set into mini batches. So you don't generally call this function. This is called by PyTorch internally. So suppose here they have given some transformation. So not much, no augmentations is there, but there's just a little bit of normalization using some mean and standard deviation. We have seen this for ImageNet, and I mean these are for ImageNet. And now you can see that the train set consists of 2000 images, val set or test set consists of 200 images, right? And correct. So now they have compiled this into this image data sets dictionary, where they have a train key which is associated with the training data, and val key which is associated with the val set, and batch size is 25. So all these are very self-explanatory, and here you can see that there's a data loader that is create. The data loader class is called here, and it's kept inside the dictionary once again, where you define your batch size, you define whether you want shuffling to be there or not, and some other parameters which we need not go into at this point. Right. Let us run these things again. Right. So this is nothing but they are just checking like whether the okay, what is there? What did I miss? Okay. This will take a bit of time to run, but let's go through it. So what they're trying to do here is nothing but this is a way so to basically go through your data loader and visit maybe one or two images from there. And so I think this will run now. Right. So here basically what this returned is one particular mini batch from your data set of 2000 images. So that is why here this value is 25. This first dimension is 25. And as I said, so this is the channel number 3, and here so because you have an RGB image, and here this is 6 because you are trying to detect the 6 objects, right? And some reverse because you had if you remember, you had already normalized your image. In order to visualize the image once again, you want to unnormalize it. That is why this reverse transform function is there, which is called when you are trying to plot the image here, right? So these are all yeah, these are not that important details. Yeah, this is where we have come to the model basically, and now we can see like we have to understand like what is going on here. I'll try to understand. If not, I'll get back to you. Okay, so stand here. Now this is only the unit model. Mm, correct. So you can see that it starts with a so whatever here if you go, yeah. So this one or this one, you can this can be a VGG16, whatever network you are using to downsample. That can be anything. That can be a VGG16, that can be a ResNet, anything. So here I think yeah, they are using a ResNet 18 model to as the base architecture, and yeah, pre-trained equal to true means they are basically instantiating the ResNet model with the ImageNet trained weights, and yeah, so these are the base layers. Correct. So now you have these layer after layer. So layer 0, layer 1, layer 2, layer 3, layer 4. So let's not, in the interest of time, we'll not go through this completely, but yeah, just understand that these represent the layers that are there as you move forward in this region. Now there's this, it's all self-explanatory. So there's this upsample. So upsample means what? Upsample means you are upsampling, you are making the resolution bigger this time. So this is basically what was happening is this is very similar to U architecture, right? So if you look at the image, so it started with somewhere big, somewhere some big point, some big resolution, It kept going down, going down, going down, going down until it reached a minimum point, and then it will go up and up and up and up and up until it reaches the original resolution. So that is why this is called a unit, because this looks very similar to a U, right? So this is, so we start with this layer 0 and we go to this layer 4, where we have reached a very very small the smallest point in the network, and then we'll start upsampling. So this is how we this is how we upsample. Now okay, so this is the crucial part. Okay. um, the output is given by this con blast. Okay, so I think, yeah, it's like I said. It's like I said to you. So this, you upsample in these steps. You go on upsampling, which means that you have now reached here, and you go on going up and up and up and up until you reach the final original point, original size. So you can see that as the name suggests, this is a this is where you have reached the original size back again, right? So now you have multiple conveys here also. So you have a this convolute once here, then second time here, then third time here. So those things are there, and now convolute means probably that is a convolution plus. So what is convolute? Let me see. Okay, convolute is this one. So it's a convolution, as the name suggests. It's convolution plus ReLU. So everything is written here with the, I mean, you can understand it based on the name that is given, but you can see here that what is going on in the con blast. So basically, you are this is again a convolution layer, where what you want is here in this parameter, this is probably the number of filters parameter. So here you are passing n class. So just like I said. So here, I mean, so these are all, so I think by mistake I don't know whether I clearly communicated or not, but here basically these are all individual conv layers, and so for each of your classes there will be a different conv layer. So as is given clearly here, so you reach up till here, so this part is common. Okay, this part is common for the entire network for all your objects, but in the last you'll require these many, I mean, there'll be a last conv layer which will consist of this n class number of filters. So that is why you'll have at the end, if you imagine, if you go through your convolution notes a little bit more, you'll understand that at the end of this step you'll basically get an activation map which is of the same size as your image, and the number of such activation maps will be equal to your n class, right? And yeah, so this is what the network looks like. So yeah, you start with the original size, then you go through the layers 0 to 4, then you start upsampling, then you call layer 3 again, because yeah, everything will be same, all the convolutions will be same here, that is why you call layer 3 again, right? And now this line basically defines your skip connection. So you are adding your x with layer 3 once again in order to not forget what you had learned before. Then you upsample again, and you upsample again, and these upsampling layers are all defined in this way, in these blocks basically, right? And similarly, you go on upsampling until you reach the original size once again. So you have now reached the original size after a lot of upsampling and first downsampling, then upsampling and adding the skip connections. And now whatever you have, you pass it through this self.conv blast, again where self.conv blast is defined in this way. So basically at the end you are passing it through a convolution layer, where you will get some, at the output you will get 64 channels. So you are passing it through 64. So yeah, uh, the target is that at the end you want 64 channels to be there. So that is how this model is designed. So remember what was our input, if we again go back a little bit. Yeah, our input was this 192 cross 192 cross 3 image, and out the label that we wanted to predict was this 192 cross 192 cross 6. Similarly, here also at the end of the network you'll also get a similar thing. So it will be like your output feature maps resolution will again be 192 cross 192 because you have reached the original size by the definition of unit, and you want to add a you want to generate 6 of them. So that is why there's a conv layer that is there that generates 6 such masks of the same size as the image. So that this is how it performs. So again, anytime, like for example, we had this confusion in the class, like what happens in the last layer of the unit. Anytime you have a confusion, please do go through media market articles or try to find the code. These models that are being taught to you, they are very very popular, and you'll find multiple articles on them, and multiple implementations as well. So nothing gives you better idea of the model than the implementation itself. So just going through the code is most of the times enough to understand what is going on. So yeah, did we run this? Yeah, cool. Next, uh, yeah, these are all again training paradigms. So yeah, so see, the ResNet unit model has been also instantiated with this number 6. So 6 stands for the number of classes. So right, they have also printed the model here. Right, so you can see that conblast is this. This is what conblast is defined by. So this is a convolution, 2D convolution layer where the number of filters is 6, so that you get 6 output maps, activation maps for each of your 6 classes. So these are just the summary. This is just the summary of the model. So again, try to learn from these how to print the model, how to summarize whatever is there in the model, and so on. Again, a confirmation that yeah, this is how it looks like. Okay. Uh, yeah, so this shape, you'll see that this is 224 because we started with a ResNet image, a ResNet model which was pre-trained on ImageNet. So ResNet is pre-trained on images of size 224 cross 224. So that is why when you print this model, the input size and output size comes out to be 224 here. Right. So yeah. Now comes what loss function do you want to train the model with, because this is the single most important part of the training, because this is how you want to train the network. So this is nothing but this is something called a dice loss, where you are doing nothing but you are kind of finding out the IOU between. So what you want is how to show you. Yeah, suppose in the yeah. So okay, let's look at here. Yeah. So for each image, in the input you have this something like this, some say 224 cross 224 cross 6 as the labels. In the output also you have predicted something 224 cross 224 cross 6, right? All you want is these two, the in given target and the predicted output, they should be as same as similar as possible. That is what you always want, and that is what you try to ensure through the loss function. So here what they do is you have this prediction, you have the target, you first compute the intersection of them. So remember that target at least is a binary mask. Prediction will not be a binary mask because you are predicting it through a softmax function. So most of the times it will not be as binary as it as the target, but the target is a binary mask. So that is why pred into target, it is a it's basically making all the places in the prediction where target, all the locations in the prediction where target was 0, you are making the predictions also 0, right? And you are summing them up. So that is meant, that is given, that you store this in this variable called intersection, and now you also find a union. So what was IOU? IOU was intersection over union. So this is intersection, and union is something again understandable. So you find the number of sum of the predictions and sum of the targets separately. That gives you a that gives you the union, and the smooth is probably a smoothing parameter that you often use in order to avoid computational overflow and underflow and things like that, right? So what you want is to maximize, sorry, okay. So what you want is to maximize this intersection over union. So just see what they have done is, so mainly whenever we calculate a loss, we do it to minimize the loss, right? So that is why, but we want to minimize the loss, but we want to maximize the IOU, intersection over union. That is why there is a 1 minus over here. So since we, when once we do this 1 minus this IOU, so you wanted to you want to minimize the loss and you want to maximize the IOU. So that is done by this 1 minus. So the moment you do a 1 minus, you do want to minimize this particular quantity. So that is why you have the loss like this. So this is called dice loss. And yeah, there are, so this is the training code basically. This is where you train the model. And okay, so these are some functionalities for training the model, but yeah, let's quickly train it. Maybe it will take some time. Yeah, it will take some time, but yeah, more or less the rest of the code is very similar to what you have been seeing till now. So it's calculating some, you know, um, so there's a binary cross entropy loss, there's a dice loss. So both of them are being used. Binary cross entropy because your um, your, what do you call it? Your target masks are all binary in nature. So you want to enforce a binary cross entropy loss on top of that with respect to the predicted values, and also you want to predict the dice loss as well. So all these calculations are done here, and then from this is the standard training script that people generally use. So you train for some given number of epochs, and yeah, I mean these are all standard basically, and yeah, it will take a lot of time, but yeah, I think I should have, yeah, it's already there. So what they wanted to do, what they also wanted to show is, suppose this training is done, suppose we have a trained model. So now suppose again you have a test set. So how does the model perform on the test set? So that is given by, so that is why they are creating this test data set of size 3, and this test loader batch size. So the data set only is of size 3, so there's a batch size of size 3, that's fine. And yeah, so yeah, all these things are there. It finds the inputs and labels from the test loader, and it passes the inputs through the model to get the prediction. Prediction is passed through a sigmoid. In order to, sigmoid or softmax, anything can be used based on what you want to do. But yeah, they want to, since they have used the binary cross entropy, they have used the sigmoid to make binary predictions at each location at each pixel location basically. So this they have done. And now in order to visualize the generated the generated masks, they are doing a reverse transform. So reverse transform, if you remember, we were normalizing the image using the ImageNet mean and standard deviation. Reverse transform is just the reverse step of that. So now they have this is the target true labels, and this is the predicted labels. So again, notice this 6 is there everywhere. So in order to match up with the number of objects, and this is what the output looks like. So these are your, this is your ground truth data. Sorry, this is your image, given image. This is your ground truth label. So you can see that all of the different objects have been marked by different colors in this ground truth label, and these are your predictions. So yeah, they look pretty similar to what is there in the ground truth. Similarly, this one is there, this one is there, and so on. So yeah, it has been trained well. Um all the objects are detected properly. And yeah, as it said here, that try tweaking the hyperparameter for better accuracy. So this is the next step that people take up, that they have a validation set. Using the validation set, you find out what are the learning, what is the best learning rate, and any scheduler that you want to use. Loss, since we have used two losses here, what would be the loss weights, and so on. So these things you can fix next. So try this out. Try taking up this step. So you already have a validation loss. Okay, it ran already. Anyway, so you already have a validation set you already have. So whatever they have asked here, try to do that. Try to tweak the hyperparameters and see, you know, whether you can get better accuracies or not. So yeah, so here you can see the training is complete, and yeah, we have started with a learning rate of this much, and they have printed the BC and the dice values as well. So yeah, so that is all that I have for today. Go through it properly so that
Ma'am, one small doubt only.
yeah, yeah, tell me.
Like even in the code, if we see at the end we will be having the six binary maps.
Correct,
So then it means we have six loss functions also, because here we can see that the way we have defined the loss function, it is with respect to each map. So
correct,
we'll be
correct,
having six loss functions.
correct, correct.
So, ma'am, my doubt is when we will backpropagate these six laws,
Huh?
then we also know that in units, some of the architecture is common for each map,
Correct.
except the last layer. Last layer is only different for each map. The other
Yeah.
layers are common. So when we will backpropagate these like loss of the cat,
Hmm.
suppose class 1 cat, when we
Hmm.
will backpropagate,
Hmm.
the all the weight will be jumbled up in some way, uh, and
See,
when
I'll tell
loss function
you.
of the dog we will
Yeah,
backpropagate
I
all
understand what
yeah.
you are trying to say, but
So,
see, this
so
is
it will disturb whole training, ma'am.
yeah, so but then this is you have to treat it just as a classification task. Okay, so suppose you were only asked to, instead of labeling every pixel, suppose you were given just normal classification task where there were six classes. So then also when there are six classes, then also for each of the classes you have a loss function, and then you have to back propagate through it. So that works out fine, right? So this is also something like that only. So just because you have to label each pixel here, that is why it's looking so different. It's looking as if you have six different activation maps, six different masks for each of the classes. I mean, one mask for each class. But it's just like a classification task only. So whenever you have the output mask, there'll be a loss function attached to it, and that will be back propagated. So and the back propagation will only be active in, suppose if you look at this one, so suppose you have this car class. So the car class is available in only this part of the image, right? And so the back propagation will happen when you back propagate for car. This will only happen in this area of the image, whereas for the road it will happen in this area of the image. So there actually will not be much jumbling up. And it is, this image segmentation is basically, as I keep repeating, it looks very different, but it's nothing but a classification task. So basically at every suppose this is one, uh, this is the mask for car. Okay, so basically most of these locations will contain nothing. Only the car locations will contain some values, and your model's work is to predict those values. So again, this is kind of a classification task only. So this is, I mean, basically this is a binary classification task. Why? Because your model has to predict whether in a given pixel location there is a car or not for the car class. Similarly, for the tree class, it will be where what to do. I mean, where in the map in the mask where the tree look. I mean, which pixels contain the tree information. So whether they, I mean, given suppose a location in the in the mask, suppose some ij, whether that ijth location consists of the car class or not. That is the only prediction that you have to do. So it's nothing but a classification task. So it looks a bit different because you are, it's looks like as if you have a very big image, big resolution. So it all kind of gets jumbled up in your mind, but it's nothing but a classification task. So backprop also will happen just like normal classification tasks do. So by what you are saying, if suppose in normal classification tasks, if we have dog, cat, tiger, monkey, all these classes, they never get distorted, right? Because I mean, backprop happens for all of them, so none of them get distorted. And uh, if you try to understand, the loss is calculated for each of those classes. So similarly, here also the loss is calculated for each of the six classes. So, and as I said, the only so what, where did it go? Yeah, not this one. Yeah. So for the car class, only this part of the mask will be activated. Only this part will have a loss. Similarly, road part will have this, only this part as the loss. So there will be no overlap as well. I mean, there will be less overlap. Overlaps will be there, but there will be less overlap. So ultimately, it will all make sense. So yeah. Okay, I think we are way past 7 today. Let's end the call. So yeah, let me know if you have any more questions later maybe.
Um, uh, uh, Ma'am, here you compared it with the traditional classification,
Hmm.
but in
Hmm.
traditional classification, we found a decision boundary usually. So that founding a decision boundary and trying to predict which class it belongs is very, I think it is very different from here, because here the entire image we are passing.
Yeah, we are passing the entire image, but basically, why I said classification is because at every pixel location, you are trying to classify whether it belongs to a certain class or not. So, like for example, why
But
I
their methodology is different,
yeah, that is
ma'am.
different.
Their
But see, that is different, but inherently the objective is still the same. You are trying to classify whether each pixel location, whether that belongs to a cat class or not, whether that belongs to a dog class or not. So inherently, it looks, the procedure is different because you are trying to do a different task. You are trying to basically you are trying to generate some image like this with different colors to different pixels. But how are you generating this? That is just by classifying only. That is by classification only. You are trying to learn like whether this given pixel belongs to a car class or not, whether this given pixel belongs to a road class or not. That is what you are trying to learn. So in that way, it's a classification task. So even object detection also is partly classification, because you are trying to, obviously, object detection, you can say rather it's a mixture of regression and classification, because you are learning the bounding box coordinates. That's a regression problem. And you are also learning like what class your object belongs to. So that is the classification part. But here there is no bounding box. All you are trying to do is you are trying to label each pixel with the object that it belongs to. So that is why I'm calling it a classification task. So it again,
thank you, ma'am.
it looks a bit different because here you are again generating images. You are wondering like how can generating an image be classification? But again, I'll ask you to go back and uh, try to think of it. As I keep saying, you have this kind of an image. Every pixel that is there, suppose you have a 10 cross 10 image, so 100 pixels are there. Take each pixel one by one, and you'll have to, your model has to say what class that pixel belongs to. Does it belong to a background class? Does it belong to a car class, tiger class, what class? So that is your image segmentation task. So this is a classification task where you are labeling each pixel with some label. And why does this look like binary classification? Because here you do not your target is doesn't actually look like this. You will, for each object you'll send a different binary mask. So there'll be a binary mask for the car class, binary mask for the road class, and so on. So each of those masks you are trying to predict. So basically, if you try to predict where your car pixels are, what you have to ideally what your model should do is oops yeah, ideally what your model should do is predict 0 for all these locations and only 1 for these locations. So that is why again I keep repeating that this is a classification task. So yeah, go back, it's, I know it's confusing, go back and have a good look into whatever articles are there, you'll get it, it will come to you. So yeah, fine, fine. Let's all leave for today. It's late. Bye everybody.